So we're back again on the topic of the quantum generative adversarial network, quantum GAN. So we basically in the last video did an overview. We did an overview on the topic and sort of the general setup. Now I think I kind of realized that those two things might end up being two separate circuits. This one being one and this one being another, just because the way they communicate is via the density matrix, which you can check out the density matrix videos as well, and you will understand probably why maybe a little bit better, because I think it's a neat way to have sort of a model that you can then optimize. Especially that's what you do always in machine learning, right? So this is point number one. Point number two is well, what I wanted to talk about today. What I wanted to investigate today is the concept of this gradient thing. So, and you know, the overall theme of this channel is really not to get into the maths deeply, but I can. And this paper is just like covered with that. But it's just funny, right? Because at the end of the day, let's try to break that through, right? So, but what this is at the end of the day, we checked that in the previous video. What a gradient is nothing else than sort of a metric or on your specific quantum state that tells you in which direction maybe it's going, or it's going to its minimum. I don't know, whatever that means, but I guess the idea is, you know, what you're trying to do with this is you're trying to minimize that. So you want to know what a gradient is, so you know in what direction to evolve the parameters. So that's kind of your learning iteration. And I'm being super fuzzy here because I'm not deep into the details myself either. But it's like, don't be. This is so funny, really. I guess that's because it's a paper. But basically, what they're trying to say here is, so they're trying to introduce a bit of a notation and how do you calculate the gradient, how that's pronounced, of a I would say maybe a quantum gate box. I don't know, whatever the discriminator is. So how do you calculate the how to calculate the gradient of these, for example, right? And so what they say is, first they introduce a way to define, okay, so how do we break down that d, right, the box d, because you'll have to break this down in order to calculate this gradient. And at the end of the day, what I'll try to do is I'll try to get a practical example as a last video on this series for the quantum GANs, because this is super abstract. It's what happens with these papers is they try to generalize that, and then that makes it super tough to get into the details here. Exactly, quantum gradients. So you see, that's what they're doing. Minimum. Yeah. So what they're saying here is basically all this blah blah here is nothing else than saying, so you've got a gate u, and then let's decompose it, and that gate u has a parameter theta, or however that's called, because that's the one you're optimizing, that parameter. And so all this is saying is, let's basically assume that your gate is broken down into like sub operations. Each of them has maybe its own parameter, which it doesn't have to be the same theta. It can be a version of it, or it can be the same in some cases. This is really a general notation. So just really, honestly, all you have to take a look at is this one, where it's like you've got a gate which is equal to this gate, then this gate, then this gate, then this gate, and each of them has a parameter. So, and that's all what that column is saying. So just forget about this. That's crazy. This notation, I mean, they have it, for a scientific paper, you got to do that, right? I guess. But it's just that brings it far away from practical usage. This notation is used to signify the decomposition of a unitary transformation and its elementary parameterized gates. That's basically what it's saying. What I just said. See, and then it says that's kind of a general form of each of those gates. Okay. So what I don't know is what a Hamiltonian is really in that context. Assuming each element is generated by a Hamiltonian. So, Mr. Google, what is a Hamiltonian gate? quantum gates by inverse engineering of Hamiltonian. Ooh. Ising-Hamiltonian formulation, Hamiltonian gate overflow, Hamiltonian. What is a Hamiltonian in quantum computing? I think I've read that before already. Quantum mechanics. In quantum mechanics, Hamiltonian is an operator corresponding to the sum of the kinetic energies plus the potential energies for all the particles in the system. This addition is the total energy of the system in most of the cases under analysis. That is way beyond what I'm trying to achieve in this. With this, it's like so. Hamiltonians for quantum computing. I probably don't want to read through all that, but in this section we consider the NOT gate based on a single qubit. It's been extensively studied in the literature. In response to which why we label it 1001 to basic states. The NOT gate corresponds to those interactions which over the time interval accomplish the following. Here alpha and beta are arbitrary. The unitary matrix U that corresponds to this evolution is okay. So maybe this is just a like a generic way. Come on. For a time-independent Hamiltonian in the diagonal representation, it yields the energy levels. That's getting too much into the physics, I think. But maybe this seems to me intuitively it's just another way of formulate a gate in terms of maybe some kind of energy levels or something like that. So assuming each element is generated by the Hamiltonian. Because I think my next video on this topic will be try to get an actual concrete example of what's going on inside those boxes. And I think that's the problem here is they're making a lot of assumptions in terms of what shape those gates have. And I think that's just they're trying to make a general expression for what those gates do. And then so they can then go ahead and do their math here, which is basically, so what they're basically saying is, they're using that expression and then they're making the derivative of the gate, of course. So they replace here the gate for that stuff, and so they make the derivative, and then they say if we define initial state and q is blah, 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 blah. It's tough to digest, really. Don't think that I understand that stuff. It's like most of the things I just read and pretend that I understand, but I don't really understand. So you're not alone there. It's just that at some point after taking a look at these things for like 5 or 10 times, you kind of grasp maybe something at intuition level. So we define initial state on q qubits. The gradient with respect to the parameter theta is then given by this. So they mathematically committed at this point. So they mathematically come up with, okay, what's the expression of a derivative? Because that's what the gradient is, really, just the derivative. As in, yeah. So, I mean, this is a bit, sadly, this is one of those things where the math really gets into the, like, it gets into the way, right? So, so derivative of a function. So this is really, and that's I consider those things basic math, but you might not, and it's fine. It's just so you understand the derivative. It's an operation that you can do on a function that tells you basically, it kind of tells you the inclination in a really rough, intuitive way of your function. So that's what they're trying to do here. Is they're trying to find that, let's say, inclination or how to find that inclination so they can then minimize it. Man, that's gonna be. I'm curious how I'm gonna make a no math summary out of all these, because it's a tough one. But that's basically what's happening here. So they do this in the maths, and then they try to walk their way backwards and say, so if this is what we want to get, what are the set of gates? What is the set of gates that we need to achieve that? And that's where you get those two things here. That's where you get that. Like, this is exactly what's happening, right? So you've got in A, we show the general structure of quantum gradients and the structure of quantum Hessians. This is something else. I don't know. The Hessians, whatever that is. At this point, it is convenient to introduce some canonical quantum gates: the Hadamard gate, the NOT gate, the X gate, the Z gate. And it's also useful to define a single qubit W gate. So that's a made-up gate by them to test this. Okay. As shown in figure 5, the gradient of a parametrized quantum circuit can be sampled from the Z expectation, the expectation value of an ancillary qubit, such that probability of being 0 minus probability of being 1. Using quantum gradients to train QNs. And that's all they say about that, because then it's already like, okay, so how do you train that? So this is not of our interest. How do they use the quantum gradients to train? That's just, I think, out of the scope of this. I'm trying to understand, because I thought that would be an interesting concept to generalize, right? So how do you make gradients? And they decompose these into J1. Then what is that? What is that? This one's going to introduce some kind of. So maybe I should read. Okay, maybe I should read that. So it says, we now have all the elements required to evaluate the gradients of 13 directly in a quantum computer. The operator P from section 2B corresponds to the Z operator of 4. Okay, what is section 2B? 2B. The operator P. I don't know. But basically it says the operator P corresponds to the Z operator of 4 when computing gradients of 4. The Z operator here. Z. Okay, it's a measurement. That's what they're saying. So it's a controlled measurement? Like, is this what it is here? It's a controlled measurement? Maybe. The parameterized discriminator D and generator G can be decomposed, okay, into ND and NG gates such that in order to measure gradients, we introduce a single qubit register grad. Okay, that makes sense. So this is what you're going to measure. This is this. It follows that all elements of the gradient of the discriminator can be evaluated for each label and sources, R and G by the quantum circuit of figure 6 with an appropriate X gate to account for the sign of the cost function. In the later case, an X gate is applied on the out D register after the discriminator to get the correct sign of the gradient. Okay, it's a technicality. the circuit that yields the gradient is this of the generator. No, of this generator. For each label is shown in figure 6b. 6b. Okay, so this is the okay, so that's how they break it down. Okay, so they break it down. No, it's a Z. It's not a measurement. It's a Z. It's a control Z. But they've totally. So apply the gain and apply. What is these, right? So it's decomposed in three like steps. First one, then this whatever Hamiltonian this is, and then this one, and that's the controlled gate. So we also see that the expectation value for each. Where was I? It's going to find the. Where was I? That's it. We know that the sign is. So basically, they just do the derivative mathematically, and then they just write this down in circuit notation, and they come up with a circuit. Awesome. But I'm not happy with that. I'm really not happy with that. It follows that all elements of the gradient discriminator. That's definitely a tough one. That's definitely a tough one. But really, what are they? So at the end of the day, what is it that they want to measure? I mean, they're going to measure like 0 or 1, and that's it. And that tells them. I think I'm gonna. What I'm gonna probably do is. What I should probably do is I should probably research, do a bit of search on that topic aside. This means independently from this paper. But maybe I'm not going to find it because it seems really ad hoc here defined. So the gradient with respect to the parameter is given by this. So the derivative of gate J with respect to parameter is, since the problem is the same concept of the derivative is always a bit abstract, right? So you kind of understand it with simple functions, but when it comes to quantum gates, it's like, what does this really tell you, right? Such that this the derivative of gate J with respect to parameter theta J is given by this. So this here, what you see here, that's what we're trying to calculate, is a derivative. How they come up with that, I don't know. Maybe based on this, right? On the definition of the gate. So I'm using the chain rule. That's the diving into this confuses me even more, because that just goes into full abstract mode and then just talking maths. So okay, so you expand and expand and blah blah. So if we define an initial state on q qubits, the expectation value of an observable. Okay, so these I just happen to know that this is probably the notation for the density matrix, because I'm working on the videos as well at the same time I'm doing this. The expectation value of an observable is the, and I think TR means trace, which is basically the sum of the diagonal of the. Sorry, it's just, that's, I'm reading this out loud, and I just don't wanna. That's not the outcome that I want to make, that I want to generate out of these sessions. I'm not really happy with this. So because basically here they just go ahead and it's like boom, that's how you define the derivative of all the. And then this point is convenient to introduce some canonical gates. Well, awesome. Because then these gates. So okay, so what I have to do is probably this has been a painful video, and there's nothing much out of it. But the next step is I'm gonna actually try to reason it from the circuit. Maybe from this circuit here. I think that's gonna be more valuable. So there's a Hadamard, and then this is kind of split into 3 steps. And there's a controlled thing here, and then there's an X for accounting for whatever, and then there's a control Z, Hadamard. Yeah. Let's see if that works.